Okay, now we're going to talk about geometric sequences. A geometric sequence is very similar to an arithmetic sequence with a slight variation on the theme, and that variation on the theme is that instead of there being a common difference between terms, there's a common ratio. We're going to actually multiply from one term to the next with a consistent value. So, for example, with the prize money option number 2, you started off with $4, and then after 1 month, it would double according to the rule given by the attorney, and then it would double again and double again. So after 1 month, you'd have $8 because you'd double, and then you'd have $16 after that, and then you'd have $32, and then you'd have $64, and this kept doubling for the 24 months. And we found out that that actually yielded a lot more money over the 24 months than depositing $2 million a month. And adding that to the balance as opposed to multiplying the balance by 2 each time. So what happens here is that there's a common ratio here of 2. We're doubling each time. We call this the common ratio, whereas before we had a common difference. And we're going to use the letter R for that common ratio in this section. So let's move on to some more formal definitions of this and work with that. So let's look at the geometric recursive formula first in this case. We looked at it last time in the arithmetic examples, but we're going to look at the recursive formula first just to get some understanding of what's happening here. So the idea is that if you look at our example down here that they use, it's a nice example, is that notice we're starting with 3 and then 6 and then 12 and then 24. It's similar to the example I gave a minute ago. Looks like the common ratio is 2, again, like the prize money example. And looks like the first term, A1, is 3. And so the way that we build the formula is we take any given term, AN, a given term, AN, and we're going to take that common ratio and multiply it by the term right before it. So this, again, this n and n minus 1, the n means the nth term, the n minus 1th term is the term right before the nth term. So this is the recursive formula, and it makes sense because we're multiplying by the common ratio each time. And of course, this kind of clarifies that right here. Common ratio times the previous term, and then we always state our first term. So the way I'd write this, just reiterating here, my first term is is 3 in this case. My common ratio is 2. So my formula is AN is equal to 3 times 2 to the n minus 1 power. And in this example above here, this makes a lot of sense because I'm basically just counting in order to find, say, the 4th term. Okay, so this is my 4th term, A4. I can just tell by looking at it. And it makes sense because then A4 would be, using the formula I have to the right, would be 3 times 2 to the 4 minus 1 power, which is 3 times 2 to the 3rd power. And that actually makes intuitive sense because if you notice, I did multiply by 3 2's to get from the first term, which is 3, to the 4th term, which is 24. So that's where we get this power. And notice the correlation. If this is a 4, then that is 1 minus the 4 in each case. So that's the recursive formula. So this allows us to create a formula that gives us any term on the basis of the term right before it. So we build this term from the bottom up, starting with the first term and building it up. Now let's look at the general formula that's non-recursive. In the last slide, you notice that they did give that non-recursive formula that we worked with at the very end there. The recursive formula was the R times AN minus 1, but they did give the general formula, and we just looked at that for a second. But this is the formalization of that, where if I'm looking at the nth term of a sequence, I take the first term and then I just count up the number of common ratios with a power. Okay, and we just looked at that example previous and saw how this actually works. And so this isn't really very difficult, guys. It just means that we can actually, I could do two different types of problem with you here. I could give you the first term and ask you to find the 36th term in a sequence, or I could say something like, here's the first term of a sequence. At what point am I going to get to 568 in the sequence? What term would that be? And you could actually solve for n in this equation. We're not going to actually do that today, but there's all kinds of ways that we could use this equation to find different values that are unknowns. So now let's take a look at an example of a common geometric sequence that you may not have thought was actually a geometric sequence. Okay, let's try this example. It's a compound interest example, actually, which, believe it or not, is a geometric sequence. You deposit $5,000 into a savings account that bears 5% interest compounded annually. If you don't ever withdraw any money or spend it, how much will be in the savings account after 8 years? Okay, so this is actually, we're going to do this in a recursive manner. But the way I could think about this is I start with $5,000, okay? And if it's bearing 5% interest compounded annually, then what that basically means, folks, is that my value is going to increase by 5%, okay? So just as a note, a percent increase of 5% means that my original value multiplies by 1.05, because 100% would be keep the value the same. So basically increasing the amount by 5% means that I multiply it by a factor of 1.05, okay? So for 5,000, I'm going to take that and I'm going to multiply it by 1.05, which is going to give me 5,250. That's year one. And so my common ratio is 1.05. So I've increased the balance by 1.05. I'm going to multiply that new balance now, because I didn't withdraw anything, by 1.05 again. So this thing is growing. So that gets me 55, 12, and 50 cents. Okay? And then I'm going to multiply that by 1.05 again. And that gets me 57.88 and 13 cents. Okay? And then I'm going to multiply that by 1.05 again. I'm trying to go 8 years here. So this would be 6077 and 53 cents. And so far, I've gone one. Let's do this. This is after 1 year. This is after 2 years. This is after 3 years. This is after 4 years. Okay. And if I actually continue this on, just for sake of time, I'm just going to give you the answer. If I actually continue this on, I would continue it on 4 more times. I would get $7,387.28. Okay. So that would be my final answer. So maybe you've never thought of the idea that compound interest is actually forms a geometric sequence, because we're multiplying by this consistent ratio each time of 1.05, because we're increasing the value of that investment by 5% each time. So in this example, my A1, my first term, would be $5,000. My common ratio would be 1.05. So that's an example. So now you're going to get to work on some examples in the flow of this lesson after this.